Hi and hello everyone. My name is HAZIQ and SHAHMEN from Group 7 and I'll be presenting the introduction and code implementation for our B-spline knot insertion assignment. So for the introduction, what is B-spline? B-spline curves are fundamental in computer graphics. They provide local control, meaning changing one control points only affects a limited portion of the curve. They are defined by control points and a knot vector. So what is knot insertion? Knot insertion means adding a new knot into the knot vector without changing the curve shape. Instead, the control points are updated through a process called corner cutting using this formula. So our task is to implement a cubic B-spline with knot insertion at t equals 0.5 and 0.9. We will demonstrate the curve shape doesn't change, and specifically for group 7, we will show how corner cutting replaces existing control points. Now let me show you how the code implementation looks like. So this program uses OpenGL to visualize the B-spline curve. And here we initialize our control points and knot vector, exactly as shown in the lecture slides. We have 8 control points and a knot vector with degree 3. So this is our knot insertion algorithm. It finds the knot span, calculates the alpha values, and computes new control points through corner cutting. So here is where we apply the formula. Qi equals 1 minus alpha times P previous plus alpha times P current. This is the corner cutting process. So I think that's all for the important part for the code. And for the summary, the program displays the original curve in red and modified curve in blue after the knot insertion. When we run it, you can press I to insert a knot at 0.5 and the console shows which control points are affected and replaces. So that's all from me. Thank you, and we continue to the next part.
Hi, my name is Chua Ling Wei from section 1. So I will explain about the B-spline. B-spline, also called as the basic spline, is a parametric curve widely used in the geometric modeling because it is smoothness, flexibility, and also local control. Unlike the Bezier curve, B-spline is influenced by a subset of the control points of any parameter values. So we have 3 components in B-splines. The first component is control points, which is point 0 until the point ends. So it defines the overall shape of the curves. So the second one is the degree, which is the P, determines the smoothness such as T equal to 3 is commonly used in the and provides the C2 continuity. The third one is the knot vector, which is defined as U, a non-decreasing sequence that controls the curve segment and continuity. The curve performs as a weight sum of control points using the basics functions. So here we have shown a basics function formula at here. At any parameter value, only P plus 1 control point will influence the curve for the local support, making the B-spline stable and predictable. So clamp B-splines the nodes at the end, so the curve starts at the P0 and end at the P end, which is the point and end of the point. So making them more suitable for CAD, animations, path, and also the surface modeling.
Okay, now I will present about the knot insertion formula. So this will introduce the cubic B-spline curve with degree 3 and the given knot vector. So knot insertion is a refined technique used to add control points to the curve without changing the original shape. So for this, the knot span is identified by locating the interval in the knot vector where the parameter value lies. So we have 2 values, 0.5 and 0.9. So this is the knot span condition for each of the values. And this is for the knot insertion at T0.5. So we insert a knot at T05 and the affected control points are P2 to P5 and we will have a new control point. So this is the original curve and this is when we use when we insert a knot at T.05. So the same we do at T0.9. So when we insert the knot at T0.9, we have the affected control points are P4 to P7 and this will result the new curve as you can see in the image here. So that's all for me. Thank you.
Everyone, I'm Chen Jie. For my part, I will do the demonstration of curve shape preservation after knot insertion. So, using the same B-spline evaluation function, the curve is first generated with the original knot vector and the control points. After inserting new knots at the t equals to 0.5 and 0.9, the curve is regenerated using the updated knot vector and new control points. From the product result, we can clearly observe that the curve before and after knot insertion overlaps exactly, and there is no visible deviation or distortion along the curve, and the start and end points remain unchanged. Although the curve shape remains the same, the control points change locally. the number of control points increases and some control points are replaced by new ones, but only in the region near the inserted nodes. So this behavior follows the Bohm's node insertion algorithm. This algorithm inserts new nodes and computes new control points in a way that guarantees the curve geometry does not change. So in this process, new control points are computed using the weighted averages of two adjacent control points, which is a P here, and the value alpha controls how close the new control points is to each original control point. Because the control polygon is refined without changing the B-spline basic function, the curve geometry remains unchanged even though the control points are modified. And that will be all from me.
Hi, my name is Lijian Ai, and right now we'll move on to the requirement variation for this assignment. So for corner cutting in B-spline knot insertion, the knot insertion does not change the curve shape, but then it will update the nearby control points. The replacement of the affected control points is also known as corner cutting. The new control points are generated along the original control polygon, making the original place that is corner cutted denser. So for the knot details that were used in figure 5.2, the inserted knot has the value of t equals to 0.5, and it lies within the knot span of u5 to u6, which is within the knot vector of 0.4 to 0.6. The affected points are P2 to P5, and the removed points are P3 to P5. The new points will be calculated and is replaced by Q3 to Q5. The alpha values for A3, A4, and A5 are all calculated through the alpha coefficient formula, and A3 equals to 5 per 6, A4 equals to 1 per 2, and F5 equals to 1 per 6. The new points are computed via the linear interpolation, and the control polygon will change, but the B-spline curve will remain unchanged. That's all for me. We'll move on to the next one. So this is our code for assignment 2, where at first it will show our B-spline that was generated by various knots, and then there's a few interactions we can do where if we press I, it will insert knot at t equals to 0.5, and if we press J, it will insert knot at t equals to 0.9, and then if we press R, it will reset to the original curve, and if we press C, it will toggle the control polygon visibility, and press escape to exit. So now we'll start the program. So here is our B-spline curve, and the red curve, which is right now, is the original, and later the blue curve will be generated after the knot insertion. So we can see here is the B-spline initialization, where we have a total of 8 control points, and then a degree of 3, and we have a total number of 12 knots, where the knot vectors are listed here. And then if we try to press I, which is a knot insertion at t equals to 0.5, we can see that there's corner cutting that was happening here, and the knot insertion where it will be lie within the knot span of u5 and u6, which will equal to the knot vector of 0.4 and 0.6, and the affected control points are P2 to P5, and alpha 3, alpha 4, and alpha 5 will be needed to recalculate so that new control points that will be lie at the corner cutting place will be generated after that. And here is the new knot vector, and the number of control points has been increased from 8 to 9. So let's try to reset it. So if we press J, it means that we will insert the knot at t equals to 0.9. So let's try it. T equals to 0.9, the knot span that will lie between U7 and U8, which is the knot vector of 0.8 and 1. And then the affected control points are P4 to P7, and alpha 5, alpha 6, and alpha 7 needs to be recalculated using the alpha coefficient formula to get the new control points that lie between the corner cutting side, which is Q5 to Q7. So the new knot vector is initialized here, and the control points has been increased from 8 to 9. So we can see here is where the corner cutting happens. Even if knot insertion happens, it will not affect the curve shapes, and it retain like that. So let's try to toggle it off, toggle it on. You can see that it's still the same. Like this is clearer. Yeah, it's all the same. So that's all from me. Thank you.
My name is AIFA INSYIRAH. So for the conclusion, this assignment successfully demonstrates the concept of B-spline insertion, knot insertion, using Bohm's algorithm. By inserting new knots at specific parameters values, we were able to refine the control polygon while preserving the original shape of the curve. The results clearly show that knot insertion increases local control by generating new control points through the corner cutting process without introducing any distortion to the curve. This confirms one of the key strengths of B-splines, which is flexibility with shape stability. So that's all from us. Thank you.